So what is it going to be? K, Q over the radius, right? K, Q over the radius. So if we were to put the same charge on both of these, the smaller one would have a higher potential. If we wanted the potentials to be the same, we would have to put a smaller charge there. But what happens is, let's look at the area. How much more charge would we have to put on the bigger one to make the potentials the same? This one would need KQ over R, and the big sphere would need K3Q, right? If its radius was 3 times as much, we'd have to put 3 times the charge on there to get the same potential. Now the potentials are the same. How do the surface charge densities compare? So this has 1Q. What's the surface? 4 pi r squared. This has 3Q, and the surface is 4 pi 3r squared. And so this one is 1/3 of the other one. You see that? In order to get the potentials the same, the larger radius of curvature, the larger sphere, has a smaller surface charge density. It has more charge on it than the smaller sphere, but it has much more area. So the charge spreads out more. So the charge density is less. So if we connected these two with a wire, or if we'd had a shape that resembled a smaller sphere on one side and a larger sphere on the other side, something like that, the tighter radius of curvature, you could view this as being the small sphere, and this as being the large sphere, right? So here you get a larger charge density. Here you get a smaller charge density to get the potential the same everywhere over the surface of the conductor. The potential, electric potential, the voltage has to be the same everywhere over the surface of the conductor. And that's why for lightning rods and things you have points. So the electric field, this is some charged object. The electric field points out like that. And where's the electric field the strongest? Where the radius of curvature is the smallest, right? And that's why lightning, sometimes you can prevent a lightning strike with a lightning rod. The electric field is so strong there, excess charge bleeds off and it prevents the lightning from striking. But if it does strike, if you can't prevent it, if it does strike, it will tend to go to the point, right, to the tip. So if you have, or if you're designing a piece of equipment with inside the equipment where if you don't want strong electric fields, you would radius the edges. You wouldn't have a sharp edge on a conductor. You'd have a radiused edge to prevent strong electric fields from building up in those areas. Okay?
I still don't quite understand why
So what happens is the question is, how can a lightning rod prevent a lightning strike? So you get a charge buildup. I forgot which one's positive and which one's negative. But your cloud starts building up charge, and your ground builds up charge, right? And when you get a big enough potential difference, the air, what happens? You get an electric field forms there, right? The air molecule consists of a positive center and a cloud of electrons around the outside, right? And those are normally attached together. The molecule holds on to its electrons pretty tightly. But in a strong electric field, the positive center of the molecule wants to go one direction. The negative cloud of electrons want to go the other direction. They get pulled a little bit. You keep increasing the strength of that electric field. Eventually you get to the point where the strength of the electric field is strong enough to rip the electron off from the atoms that hold it. You've ionized them, right? You've stripped the electron from them. And the air, then we say it's broken down. It's no longer an electrical insulator. It's become a conductor. Once those ions are separated from the atoms, then they can move, and it becomes a conductor. And that's your lightning path, right? I don't have purple. You get this, your path where charges flow. Okay, so what does a lightning rod do? You put a lightning rod in, and you create this very strong electric field right here. And some of these charges, that electric field is so strong, some of these charges then can dissipate into the air, and you can get some of the charges to bleed off of what's on the ground, the building, the ground, whatever it is. You can get some of those charges to bleed off and reduce that potential difference between the clouds and the ground, the clouds and that object. It depends on how quickly this separation is taking place. I have two Van de Graaff generators. The Van de Graaff generator, you remember, is the one where we tried to get somebody's hair to stand up, didn't work. I have a small one. It doesn't work that well. It builds up charge not that quickly, right? And we can get it to form sparks. We can get the air to break down around it, maybe an inch or so. If we put a pointed needle on top of it, it won't make sparks anymore. We shut off the lightning it makes when there's a grounded sphere next to it. It won't arc to it anymore. It bleeds off the charges, prevents it from causing lightning. The bigger one I have, it's a better one. The belt goes a little faster. It's a little bit bigger. We put the needle on top of it, and we can't prevent lightning from striking to a grounded sphere next to it. It'll still strike. It builds up too quickly.